second video for exam number 7 for Math 107. And this is the last chapter test before the final. For number 11, you need to use the Greek sigma and write the expression for all the positive even numbers and all the positive odd numbers. I want you just to know this. It's just a memorization thing. The even numbers are 2n, where n is any natural number. To see how that works, let n be, what you call them here. Here's n and here's 2n. Let's n be 1. 2 times 1 is 2. Let n be 2. 2 times 2 is 4. 3. 3 times 2 is 6. 4. 4 times 2 is 8. As you continue, these will only be the even numbers. As n gets bigger and bigger, so does this list. You don't have to worry about infinity or cardinality in this class. But the way to get all the even numbers is 2n. That's the abbreviation for them. How about the odd ones? It's just 2n minus 1. I'll add a column over here to show you that. 2n minus 1. Well, 2n is 1, minus 1 is 1. Instead of the 4, I have a 3. Instead of the 6, I have a 5. Instead of the 8, a 7. You see, these are all odds. So if this is even numbers, is 2n. Odd numbers is 2n minus 1. I want you to memorize that. You will see it again. You'll see that again quite a bit in mathematics as you go on. And the sum of all of them means you start at 1 and go to infinity. Start at 1, go to infinity. And that's all the positive odd numbers and positive even numbers. Now we're back to sequences again. Write the definition of an arithmetic sequence and give, that means make up, an example. Alright, an arithmetic sequence is one in which there's a common difference between each term. You can write that in words to give the definition of it. You say there exists a D, such as if you subtract the neighboring terms, you always get the same number, and that number is D. Okay. Another way to define it is just to write the recursive definition. That also defines an arithmetic sequence. And then you, of course, make up an example. And now for a geometric sequence, there's a common ratio. This R is a common ratio. That means if I take the two terms of the sequence, two neighboring terms, and I divide them, you're always going to get the same ratio. So R is going to be R3 divided by 2 will give you that ratio, that number. A16 divided by A15 will give you the same number, the common ratio R. That's because each term is really just multiplied by that R to get the next term. This is a big example from compound interest, but we could have a simpler one. Let's say R is 3, and I start at 1. The next term is 1 times 3, which is 3. 3 times 3, which is 9. 3 times 9 is 27. You see, there's a multiplication going on. And if you made fractions, 3 over 1 would be 3. 9 over 3 would be 3. 27 over 9 would be 3. Okay. So that is a geometric sequence, and then you can make one up. Like I say, this is one from compound interest with $1,000 as your principal. And here are the various account balances. 1.06 means that the 6% interest was combined with the previous amount and placed into the account. This is the expression for compound interest. A is the amount in the account, P is the principal, and it's 1 plus the annual percentage rate written as a decimal divided by the number of times per year the interest is compounded. If it's compounded quarterly, then it's compounded 4 times a year. So the K that's your value for K. Alright. The annual percentage rate is 5%, so the R you write as 0.05. And KT is up here as the exponent. K again is the 4. So the 4 appears here, and it also appears up here. And T is time in years. Alright. So now if we work out the term in parentheses to simplify our life a little bit, it's 1 plus 0.05 divided by 4. It's 1 plus 1.0125. So that's everything in parentheses, so we don't have to worry about it anymore. We're looking at each quarterly amount. We'll let T be 1/4 because it's a fourth of a year. Every fourth of a year, the interest is added to our account. All right. Here's a list of the terms. Initially, you start off with just the principal in the account. By the time you get to the end of the first compounding period, at the start of the second one, the principal is multiplied by 1.0125. The 0.125, of course, gives you your interest part, and the 1 is that you aren't taking any of the principal out of the account. At 3, you've got the second one times 1.025, which is the principal times 1.0125 squared. So what you found for this term, as you go up, it continues, the exponent increases, and because of the way we have the counting here, it's always 1 less than the exponent. If we started this list at 0, we would have a match up better. Here's the general expression right here. For the pile of logs, if there is one fewer log in the layer, in the next layer, and the layer up, this is an arithmetic sequence. Of course, it looks like this: 35, the next one's 34, 33, etc. How can you write that? You could specify it as, well, it's really subtracting. So the first term, the first row has 35. That's the first term in your sequence here. The next one is the previous one minus 1, because this 33 is 34 minus 1, subtracting 1 from each one as you go up. Or you can combine all this into one definition. You could say AN equals A0. Oops, I'm sorry. Let me write it better. AN equals A1, the starting amount, minus 1 times N minus 1. In this case, it would be 35 minus 1 times N minus 1. So that's your definition, your recursive definition for the sequence made up of the layers in the log pile. There will be a question on calculating the number of number of logs in a log pile, or I think there's another one on there. I change them around so I forget. But you get no credit for just trying to add up all the numbers. There's 30, for example, in this pile of logs, starting at the bottom, you have 368, 367, all the way up to 10. You get no credit to trying to add up all those numbers. You need to use a formula. The formula is in the reference section, but it's not identified. You have to know what it means. For arithmetic sequence, the sum over the first n terms is n, the number that you're trying to sum up over, okay, times the first one plus the last one, that would be the bottom layer, plus the top number in the top layer divided by 2. And usually some of it's easy to figure out and some of it is not easy to figure out. In this case, you know A1 is the 368, that's the number that's in this layer, and the top layer has 10. Okay, but how many layers are you summing? You'll have to remember that the total number of layers here would be, since it's moving only by 1, would be 368 minus the 10, the top layer, plus 1. And if you count on your fingers, you'll find out that's right, and this becomes 359. And that's your problem. So the most important thing here is to grab the right formula. You get a lot of credit for grabbing the right formula. Then fill it in with what you know already. You already know this, you know this, of course the 2 is given. The part that's hard to figure out is the 359, but make an attempt to do that. In this proof by induction, this is one of the 2 problems that was proved in the homework. So if you look at this again and you review the homework, you should have it. To prove by induction, you first say, does this hold when n equals 1? When n equals 1, you go to this side and grab the first term, and then you put 1 for n in this other side. So in this case, it's 1. Is it equal to 1 squared? Yes. Now go to step 2. In step 2, you assume that this formula is true when n is equal to k. K just being some arbitrary number. You need to get a different index in here. So write it out. 1 plus 3 plus 5 plus all the way up to 2k minus 1. Remember, I replace all the n's with k's equals k squared. Then I ask, does it also hold if I advance the counter to k plus 1? So I'm going from k to k plus 1, and can I still make it hold? This is where we're trying to see if the dominoes will fall over and each one will hit the other one. Okay, so when I write this out, I have to go all the way up to the k term and then add on the extra term. That's what the plus 1 means. Add on the next term. It's 2. You put the k plus 1 here and here because that k plus 1 is replacing the in. But the rest of the sequence, the rest of the series, sorry, is still right here before it. It's still intact. Nothing happens to it. Okay, be sure to use parentheses. Okay. Now, the trick on the 2 that I have given, let's go to a different color, is that all the terms up to here are the same here, and because of my assumption that it's true, they equal to k squared. So you can replace all this green underline with just k squared. Now, work out, that's it for the math part, for the induction part really. And just work out the algebra and see if both sides are equal. And when I work out the algebra, I find out that on each side I get k squared plus 2k plus 1. And then it is true and it holds.